So the section 6.2, it introduces 8 lemmas. So basically I will introduce the relationships between the 8 lemmas. So our goal is to obtain a unique P matrix. That's the limit of PK. But we must show that it's independent of the initial condition P0. So the only condition for P0, so P0 is non-negative. So that's the only condition for P0. So the first step, so in this book, it shows that first you have to assume that the linear system, the 6.1, is this one. So this system is observable. So that's one of the conditions. So one condition to make sure the system is observable, that is the matrix. So the matrix has C and CA until CA minus 1. Sometimes we also call this matrix is observable matrix, observability matrix. Okay. So if this matrix is full rank, then the conclusion is that there exists a non-negative definite symmetric constant matrix W. So W is independent of P0. Okay? So such that the other PK are upper bounded by W for all K is greater than N plus 1. Okay. So here is the proof of lemma 1. So I will not show you the proof, but there's in the proof, there's something very interesting. It's about how to construct a linear estimator. So also the linear estimator is unbiased. Okay, now let me show you how to do this, because this is very interesting. So let me show you it using the whiteboard. So this is how it works. Okay, so first let's get the recursive of the system. So let's assume we want to estimate xn. Okay, if we want to estimate xn, okay, so let's first start from x0. Okay, so we want to estimate x0, then we estimate xn. So based on the recursive relationship, we know x1 is equal to a x0, then plus gamma c0. Okay, so we can continue. You know, x2 will be a x1, then plus c gamma c1. Okay, we'll do one more step to replace x1 by this expression to have a. So a x0 plus gamma c0, then plus gamma c1. Okay, then it will be a squared x0 plus a gamma c0 plus gamma c1. So we can continue. Then in general, we know xn. So xn, it will be an x0. Then we plus some noise. Okay, if you continue, because you have to pay attention that this is all linear combination of the noise. It's a linear, okay, plus some noise term, but it's all linear. Okay, so this is very important. It's all linear. Okay, then let's see how can we first estimate x0. Okay, now let's look at the output. If we start from y0, you know, y0, it is c x0 plus it 0. Okay, so we know then y1 is c x1. Okay, so c x1, then we use this expression. We know it's c a x0, then c gamma c0, then plus it 1. Okay, so this c x1, so this part is x1, then it 1. So let's do one more step. Okay, so it's y2, or let's erase. Okay, so y2, you know, y2 is c x2 plus it 2. Okay, then we use this expression. Okay, replace x2. We know we have c a square x0, then plus c a gamma c0, then plus c gamma c1, then plus it 2. Then we can continue until we use yn minus 1. Okay, so yn minus 1, we use this pattern. We know it will be c a n minus 1 x0, then plus c a gamma c0 until, I think here should be n minus 2, but continue until c gamma c n minus 2 plus it n minus 1. Okay, we follow this pattern. But if I write, so let's erase this part. Okay, so if I write the observation matrix, okay, write all the output in vector form. Okay, you'll see what happens. Okay, if I write it's in vector form here, then we have y0, y1 until yn minus 1. Then you see here we have ca until ca n minus 1. So this is the observability matrix. Okay, so the x0. Then again you see other terms. Okay, it's all linear terms of the noise. Okay, similar to here. Okay, just some noise. Okay, we don't care about what's the noise. Okay, it's just some noise. Okay, also it's linear. It's no cross terms. It's no multiplication of any of the two noise. Okay, so it's just a linear of the noise. Okay. Now let's denote this the data. Okay, maybe in the book it's used V. Okay, let me change to V. It's not Y. Let's use V bar to represent this vector. So this is the observability matrix is N. So now let's multiply N transpose. Okay, so multiply N transpose. Okay, this is a noise. Okay, then we know because this N matrix is a full rank. So N transpose and N is non-singular. Okay, therefore, we can get x0 is equal to n transpose n inverse. Okay, the inverse always exists. This n transpose n inverse, then n transpose, this is the v bar, or the data we have. That's the observation from the output. Then minus some noise. Okay, there's still some linear of the noise. Okay, then if we put x0 into this equation, we have xn is an. So this part is n transpose n inverse n transpose. That's the data. It's a linear of the data. Okay, it's a linear of the data. Then minus an some noise, because a is a constant. Okay, so this linear of the noise plus another noise. Okay, this is all linear of the noise. Now we can get a linear estimation. Okay, also it is unbiased if we assume all the noise has zero mean. Okay, if we make estimate, xn height is an n transpose n inverse n transpose v bar without the noise. Okay, so then this one is a linear estimate. It is also unbiased. But what assumption we made about the noise? You see, even though it's not minimum variance estimate, but we have minimum requirement about the noise. Because there's no cross term, we only need to assume the noise has zero mean. Okay, so this is one approach to estimate xn by using linear estimate. It is also unbiased with minimum requirement about the noise. Okay, we only assume, okay, the noises have zero mean. Okay, if we go back to the book, okay, you see what the requirement in Kalman filter for the noise. Okay, so if you use the one I just showed you, see, all the assumption can be removed. Okay, we do not assume it is Gaussian, not even it's wet. Okay, it could be colored noise. Okay, we only require zero mean. Okay, we do not know any about this covariance matrix. Okay, even though we have no cross term. Okay, this is two random variable, the C and E, they could be correlated. It doesn't matter. Okay, so this is the one thing about this estimate. Yeah, this is in the book. It's a linear in data, and it's also unbiased. Have minimum requirement about the noise. Okay, so lemma 1 basically tell you that this pk is upper bounded. Okay, it's upper bounded. Okay, but let me use another whiteboard. Let me clear on my drawing here. So basically, lemma 1 just tells you that pk. So this is the lemma 1. So lemma 1, 6.1, it just shows that it's bounded, bound pk. So pk is bounded. It just shows that pk is bounded. Then we look at lambda, but you also need to pay attention that here the pk could be the p0. It could be any p0 unless it's non-negative. Okay. Then we have this lemma 2. So lemma 2 tells us about if you consider this phi, the definition of phi is here. If you consider this phi as a function of a matrix, then this function is monotonically increasing. It's a monotonically increasing function. So in the matrix sense, if P and Q are both non-negative definite and symmetric matrix, if P is greater or equal to Q, then phi P is greater or equal than phi q. Okay, so I will not show you the proof, but there's a very interesting result about this formula. Okay, if you assume this matrix, if the matrix in the one of the, or some of the entries in the matrix, it contains some variable s, then the inverse of the matrix, then you take derivative with respect to s. So this formula is minus a inverse s, then derivative as to s result inverse, then times the a inverse s. So here it's the lemma 2. So lemma 2. So lemma 2 just shows you that. So this is the lemma 6.2. It just shows you the monotonicity of phi. Okay. So this phi. Okay. So this is the phi. Okay. It doesn't show you the monotonicity of, okay, this is the CITY, okay, monotonicity of the phi, not the monotonicity of the PK, okay. But this is based on, now let's go back to the book. So this shows the monotonicity of phi, this function. Then let's go to this lemma 0.3, okay. So lemma 0.3, it shows how to use the lemma 2. You assume the same linear system, still the 6.1. Then let's assume the initial condition. Let's fix the initial condition. Let's P0 be 0, okay? Then we can apply lemma 6.2 to show the sequence of PK, convert this component-wise to some symmetric matrix. P is non-negative as K goes to infinity, okay? So I will not show you the proof. So here, you just use the lemma 2. Here, you use the lemma 2 by assuming P0 is 0. Then you get the lemma 6.3. So in this case, you showed the monotonicity of PK, but this is under the condition of the P0 is 0, okay? Now it has some similar result, okay? You see this PK is upper bounded and it's monotonically increasing. Then we know the limit, okay? So the limit exists, okay? So this, we know the limit exists. So the limit exists. Then let's go back to the book. Now let's jump to 6.5, okay? If the limit exists, how do we find the P, okay? Because we want to assume, so no matter the initial condition P, they all convert the P0, they all convert to the same P. So how to find the P? We can just pick an arbitrary initial condition P0. The simplest one is to pick P0 is 0, okay? The lemma 6.5 is just to find the P, okay? Find this P. So this is the recursive relationship of PK. Then for an observable system is P0, then you find P0 is 0, you find this P, the P matrix satisfies this equation, okay? Then we know the lemma 6.1 and lemma 6.3. So guarantees the existence of P. Now we find the P. How to find the P? We let P to be 0. Then this is the lemma. It's the lemma 6.5. Okay. Basically, you find this P. Then let's go back to here. Okay. Since we find the P exists, then the same for the G matrix. So the GK is defined in this equation. So G will be also, the limit of G will also exist. Okay. So in the first part, we assume the P0 is 0. But next, we want to show for any non-negative definite symmetric matrix P0 as an initial condition. So PK still convert to the same P. Okay. Then from here, we just assume this P0 is arbitrary non-negative definite symmetric matrix, and the PK satisfy this recursive form. Then we need the lemma 6.4. So lemma 6.4 it says let the linear system 6.1 be observable. So P can be defined using lemma 6.3, the same, but it's also lemma 6.5. Okay, 6.3 and 6.5. Then we have this following relationship in this recursive form. It holds for all k is 1, 2. Then, because you think in control, if you think this as a dynamic system, okay, then this similar like a recursive, the difference equation. If you assume this is EK, so this is the EK minus 1. Okay, it's similar like how do we prove the system is stable, but this is a matrix form. Okay, then eventually the book didn't use the form of 6.9. Okay, it used a different form that is 6.25. Okay, just you use 6.9 repeatedly, so you have a different form. So this the one will be used in the book to show the proof. Okay, similarly, okay, it's a recursive form. Okay, now we want to show the convergence of PK to P. Basically shows, so this will convert to 0. Okay, it's similar like the stability of a system. So let's go back to here. Then basically you from lemma 6.5. Okay, you want to you're using lemma 6.4 by writing it in arrow form. Okay, it's an arrow form. Okay. Then in this form, we need to first, the book shows, so this part is bounded. Okay, so show this part is bounded, you need the lemma 6.6. So this lemma 6.6. So let the linear system 6.1 be completely controllable. Okay, so that's the matrix. So the gamma A minus 1 gamma So similar, this is called controllability matrix. So this is the controllability matrix. Controllability matrix. So if the system controllable, one condition is controllability matrix is full rank, then for any non-negative definite symmetric initial matrix P0, we have PK, it's strictly greater than 0. For all K is greater than or equal to Kn plus 1. Then because of that, we know P is strictly positive definite, okay? By using lemma 6.6, let me go back here. So by using lambda, the lemma 6.6, then together you also need, so the lemma, you also need lemma 6.1. Okay. So together with these three lemmas, okay, then you can get this. It will give you this lemma 6.7. Okay, lemma 6.7 says the linear system is observable. Then the BK B transpose is less than M. M is constant matrix for all K is greater than N plus 1. So then each element of BK is also bounded. Okay, the absolute value is bounded by some constant M for all I, J, and K. Okay. So here the BK is bounded. This lemma 0.7, this lemma 6.7, it shows the BK is bounded. Then last, we want to show the eigenvalue of this matrix is less than the absolute value of the eigenvalue of this matrix is less than 1. That will be 6.8. Okay, like lambda be an arbitrary eigenvalue of this matrix. So if the system is both controllable and observable, then the absolute value of all eigenvalue of this matrix is less than 1. Okay, so this lemma 0.6. So this lemma 6.8, it shows this the absolute value of lambda is less than 1. So together with all this, you have in the error form, so one term is bounded, similar like the system stable, then you show that the PK you convert to P for any initial condition P0. Yeah, that's basically about this section 6.2.